Okay, so last time we stated the Cauchy-Binet theorem, but let me just give you a brief review what we learned last time. So Bessel-Vienna lemma, we have a graph, directed graph, and starting and ending points given. So matrix ij entry is a generating function for all path from ith vertex starting point to jth ending point. And the determinant, what the theorem says is that the determinant of this matrix is the generating function for all non-intersecting lattice path from the starting points and ending points. They can be permuted, but we have to multiply the sign. And we prove the theorem. And this is something that the last example we covered. When we have this kind of trivial graph, we have n vertices, n starting vertices, n ending vertices, and nothing else. And every starting and ending point between them, we have an edge. So with weight Mij. Then the Bessel-Vienna theorem is exactly the determinant expansion of the matrix. But this can be used to prove the Cauchy-Binet theorem. The minor, we also define the minor. We have a matrix like this, and this is the set of all subsets of size, or subsets of M of size K. And when we have two subsets like this, then the minor of a matrix is defined to be the determinant of the matrix that you can get by selecting only those in the chosen indices, the rows and columns. So the theorem that we want to prove today is the Cauchy-Binet theorem. This is a quite useful theorem, and the statement is that we have two matrices of different sizes, N, L, L, N. So they are kind of opposite like this, so that we can multiply them. Their multiplication is a square matrix, so we can compute the determinant. And the determinant can be computed as a sum over some minus like this. So that's the statement. And we will prove, let's prove this then. Proof. So the important part is the setup. Once you set up everything, so most of the time, if you use Bessel-Vienna lemma, the LGV lemma, the difficult part or the crucial part is the setup. If you have set up everything, then most of the time the result follows just quite easily. So the setup is the most important thing. So let G be the directed graph. Is it okay? Can you read the text? Directed graph. Where is it? Yeah, with vertex set A1 dot 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 AN, B1 dot 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 BL, and C1 dot 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 CN. And edge sets are, let me just draw this diagram. That'll be easier. So we have A1, AN. We have our B's, B1 up to BL, and finally C1 up to CN. I think so, two things. So, and basically you connect everything here. Everything here, they're all connected. And the weight is AI BJ is, let's define this to be Mij. So we're going to define a matrix. BICJ equals NIJ. These are given, so we define the weights in this way. Okay, we put the weight. So just it's a diagram is not very good. So for example, here this is AI, BJ, this is like MIJ, and here this is say BRBS, CS, then this is like NRS, like that. Okay, so situation is like this. Then let L be the matrix. Given by Lij is the generating function for all paths from AI to Cj, the weight of path. Okay. Okay. Yeah. Then, how can we go from AI to say a Cj here? You can use any of these B's. So you can either use B1 or B2, anything. But once you choose B, you have to go only one way. So this is the sum over all K from 1 to L. If you choose K, then weight P is AI BK, and the weight of BK CJ. Well, what is this? MIK and KJ, but this is exactly the IJ entry of the product of this matrix. Okay. So L is basically the matrix that we have in the left-hand side. And now let A be the set of vertices, sequence of vertices. C, it should be C. Then, by the LGV lemma, determinant of the matrix L, because the matrix entry is the generating function for all path from ith vertex to jth vertex here. You consider all the non-intersecting lattice path. Generate sum over all this n tuple of non-intersecting lattice path, A to B, with sign. This is a boldface P, and the weight of the boldface P, so meaning there's a tuple, it's an n tuple. But what does an n non-intersecting lattice path look like? You have to have an n path. So here you go something like that. Here you go something like that. This is non-intersecting as long as the intermediate vertices are all distinct. But of course, if you share the same vertex twice or more, then it's going to be intersecting. So all that matters is the intermediate vertices are all distinct. So every non-intersecting path, say P1 ... Pn in this set, is of this form, is something like this. Pi must be a path from AI to let's say, maybe I can just write down exact is of this form, let's say. So it's a path, so it goes from AI. The ending point can be anything. So C, say sigma I. The ending point must be all distinct, so it can sigma I. But here, it can be anything, B. But I'm going to use this notation. It's a little bit technical. It looks a bit technical, but sigma I, tau I, where I is a subset is a subset of, we have L possible vertices, but we have to choose N among them. So, and then I'm gonna say, okay, maybe I'm gonna label them, all the numbers, I1, IN. Okay, so they are all distinct. And just to make sure it's super clear, they are all increasing order, okay? That means here we select, so here is the indices that we choose is going to be I1, I2, etc. Okay, IN, we choose them in the increasing order. But of course, this doesn't have to go to the ith element here. It can also be permuted like that. Right. In this case, what is the sign? What is the sign of the end path? The sign is determined by the ending vertices. So it's going to be the sign of the sigma. The sign of tau doesn't matter here. Okay. So we can rewrite the formula in this way. So a determinant of L equals sum over, because we can sum over all this Ln, and we have two parts, like a sigma, a tau, Sn, sigma, Sn, and we have to multiply this sign, and then product the weight of the path. So we have n path, so it's like this, but the path is this, so the weight is the product of this weight and the weight of this. Okay, so it's weight of ai comma bi tau I, and weight of bi tau I comma c sigma I, like that, right? Now all we need to do is to rewrite this so that this, just try to simplify this. Try to simplify. And first of all, yeah, I'm gonna omit the details. So, and as tau. But here the idea is we want to rewrite, instead of sigma, I'm gonna write sigma as can I say rho tau. I'm going to introduce another permutation. So in other words, rho equals sigma tau inverse. So instead of summing over sigma, I'm going to sum over rho, where rho is sigma tau inverse. And then sigma is now rho tau. And here I from 1 to n, ai bt bi tau I, tau I, sigma, sigma is a rho tau, like this, okay? But we can separate this. This is the product of two signs of two permutations. So sum over tau, sigma tau, sine of tau. Right. Sum over rho, sine of, rho. Or maybe I can, I'm going to move this part over here because it only involves tau. And then this sine and then product weight of I did nothing but just rearrange the terms, the vectors. But if you look at this, carefully, you take the product of all this, right? For I goes from 1 to n. So this is like this. If I goes from 1 to n, this is basically just 1 to n, but all in some different permutation. But the product is, of course, commutative, so the order doesn't matter. That means you can just ignore this. You can just pretend that this is just I. This is just I. Because the product is just commutative. So what is this? But this part is, by definition, is a mi weight from the weight between these. So it's m I tau I. This part n I tau I. N I. Sigma I. But this, now if you look at this part, this is nothing but the minor of the matrix with i's are all in possible integers from 1 to n. But here you only select possible entries from I. And same here. If you look at this part, this is exactly, including the sum, this is exactly n, where row indices are from I, column indices are all of them. Okay? Make sense? But that's exactly the right-hand side of our formula over here. That's the proof. That's the proof. So, yeah, you may think this computation is complicated, but this is just a very standard and just routine computation. So once you set up everything, all the proof is just follows quite naturally. So that's the idea. So Gessel-Vienna lemma also proves the Cauchy-Binet theorem. Okay, so that's the section for the Gessel-Vienna lemma. Now we're gonna move on to the next section. It's about Hankel determinants of moments. Okay, so as usual, we're gonna let this to be an monic OPS with moment mu n such that they satisfy this three-term recurrence. Okay? This is our usual situation. And the definition of Hankel matrix is the following. So the infinite Hankel matrix, the Hankel matrix H of the sequence mu n. So it's defined on a sequence indexed from 0. So whenever you have a sequence like A0, A1, dot, 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 and Hankel determinant is defined. So for in our case, we're going to use the sequence of moments. This is matrix H, denoted by H, and it's the infinite matrix, where the ij entry is the moment mu sub I plus j. So ij from 0 to infinity, like that. So it's an infinite matrix, like that. So it looks like mu 0, mu 1, mu 1, mu 2, mu 2, mu 2, and it goes infinitely like that. So it's anti-diagonal entries are the same. Okay, then the Henkel matrix, Henkel determinant of size n, the Henkel determinant delta n, denoted by delta n, is just the minor of the Henkel matrix, where we take the entries 1, 0 up to n and 0 up to n for both rows and columns. So in other words, it's the determinant of the matrix mu I plus j, where ij from 0 to n. So if you want, this looks like mu 0, mu 1, dot, 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 mu n, mu 1, mu 2, dot, 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 mu n plus 1, and mu n plus 1, dot, 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 mu 2n. It looks something like this. So this is the Henkel determinant. We actually, we saw this when we studied orthogonal polynomials at the beginning of the semester. And yeah. So how can you compute this Henkel determinant? That's the something that we want to do. And we know that what is the entry? Mu ij, mu sub ij. Mu n is the generating function for Mochkin path of length n. So this is the generating function for Mochkin path 0, 0 to I plus j, the weight, the usual weight of our Mochkin path, say p, like that. But because we want to consider this matrix, we define the starting and ending points in a nice way so that this is a nice system of lattice path. So idea is, instead of starting from 0, we modify the initial point and ending point. So the idea is this. A, this will be the starting point. B, ending point, where ai is minus I comma 0, bi I comma 0. So in other words, this is 0. The origin in the real axis is a0, b0. So here a1, a2, like that, b1, b2, like this. Okay. Then, of course, mu ij is the generating function for Mochkin path from let's see, Moch ai to bj, because the length, the distance between ai and bj is exactly I plus j. This is how we set up the things. Okay, so weight of p. Therefore, by the LGB lemma, determinant, Henkel determinant, which is the determinant of mu ij, 0 to n, is the generating function for all non-intersecting lattice path. By the way, because when we talk about LGB lemma, we have to define the weight, a directed graph with weights. And then the graphs, the directed graphs are exactly the graph that will allow us to create Mochkin path. That's basically the idea. So, but if you want, we can, to do that, if you want a kind of rigorous definition, you consider all the grid in the upper half plane, and you can go either this way, this way, this way. So you draw all these edges like that. You draw all these edges. Then this is our graph. It's an infinite graph, like that. So then in our system of this directed graph, this is all non-intersecting path from A to B with a sign and weight, like that, okay? But here, an interesting thing happens. So let's consider n equals, say, 3, and see what we can do. So we have this graph, A0, B0, A1, A2, A3, A1, A2, A3, B1, B2, B1, B2, B3, like that. So we want to go from these 4 points to these 4 points without any intersection points, okay? But of course, this is both a starting and ending point, so this must be the single path of length 0, so we must have just one path here. Now, we have to go, this must be another starting point, so we have to start from there. And then we have 3 possibilities, but of course, you cannot go below. So we have go either up or horizontal, but this is impossible because this is already occupied, so we have to go up. This is only possibility that we can go. And what about this? Again, this cannot go horizontal, so we have to go up. Same here. But then this cannot go horizontal, cannot go down because these two are already used, so we have to go up. Same here, it has to go up. And this must go up like this. So these are all decided. Now we have to go all of this. But if you want to go from one of these, this is the only possibility because these cannot go there. So this is fixed. This is the only way you can go to, you can reach B0, B1. And this is the only way that you can go to B2 because the grid is something like that. You cannot, this is the only possibility. This is the only possibility. So this is unique. This has a unique element like this. What is the weight? And 0 goes to 0, 1 goes to 1, 2 goes to 2. So the permutation is the identity permutation. So the sign is plus. And what is the weight? We only have weight for the down steps. Lambda 1, lambda 1, lambda 1, lambda 2, lambda 2, lambda 3. Weight, sign, so let's say P, sign equals 1, weight equals. If there are n here, you have n lambda 1s, the n minus 1 lambda 2s, etc. So it's like lambda 1 to the n, lambda 2 to the n minus 1, lambda n to the first. This is the only one. That means we just proved that this theorem, very nice theorem, the Henkel determinant is just a product of all the lambdas. But if you remember, we proved this using the orthogonal polynomials, but you can also prove this using combinatorics only. Okay, so, but if you remember, our goal at the beginning of this chapter I mentioned, our goal was to express lambdas and b's using moments only. So actually here we can express this using mu only, but we will do this later. But before that, we will find something related to Henkel matrices and b's. But here you see there's no b, so we have to modify the matrix a little bit. So now define delta n prime It's a slight modification of the Henkel determinant. So we use the same matrix, Henkel matrix, but we select the same rows. But for the columns, we increase the last one by 1, like that. Yeah. I think our notation was this. Our notation for the, like this. So it's exactly the same, except we increase this by 1. And let's say this is the entry is Mij, say. Okay. Then, so in other words, Mij is exactly mu I plus j if j is less than n, but mu I plus n plus 1, say. Now maybe I can just write it this way. Mu n I n is mu I plus n plus 1. So the last one, for the last column, we just have a 1 plus. All right. So to model this lattice path, this determinant, we define A in the same way. And then, but B, let's say B prime, B0, Bn, where Ai is the same, minus I comma 0, but Bi, Bj, I think I can use I, is I, but plus 1 if I is n. This is the notation for that. This means the Kronecker delta. This is 1 if these two numbers are equal and 0 otherwise. So this means I if I is less than n, but n plus 1 if I equals n. Then of course, by the setting, this is exactly Mij is exactly the generating function for Mochkin path from Ai to Bj by the construction. So this is the definition, determinant of Mij 0 to n, but by the Kessel-Vienna lemma, LGV lemma, determinant is equal to sum over all non-intersecting lattice path from A to B prime, the weight assigned, and weight, like that. Okay. And now let's consider this. What are the non-intersecting lattice path? So n equals 3 example. So 0, A3, A. Oh, sorry, A. Oh, I think there's a A4, A3, A2, A1, A0. I think this is B0, B1, B2, B3, but B4 is here, like that. Okay. So we want to go from these 5 starting points to these 1, 2, 3, 4, 5 points. Again, this is fixed. You cannot do anything but just have an empty path. And again, this is fixed. This is fixed. This is fixed. And this is fixed. Okay. Now again, this is the only way that you can go to B1. This is the only way that you can go to B2. This is the only way that you can go to B3. But for B4, if you want to go to B4 from here, there are several choices. So you can go either horizontal, because now you can use, notice that you have to use one horizontal step, right? Because the length is 2n plus 1, so you have to use, but we already used n up steps, so there are n down steps, so one horizontal step missing, so we have to use. You can go either this, or this, or this, etc. Right? So there are, so in this case, there are in total n plus 1 possibilities, elements in this non-intersecting path. And what are their weights? With weights, they all have sign 1, because AI goes to BI for every I. So sign is the identity, sign of the identity permutation, so it's 1. And weight, but weights are different. Notice that we always have lambda 1 up to lambda n for the last path. So the down steps, we have exact same set of down steps like this. So the lambda weights are exactly like delta n. But we have some b's. But this can be, the horizontal step could be bn, or bn minus 1, or bn minus 2, etc. or up to b0. So weight, delta n bk, where k is from 0 to n. So we have n plus 1 possibilities. So what we have proved here is that, is this theorem. I can just now state the theorem. Delta n prime equals delta n, all the weights, product of the weights of the down steps, and b0 up to bn. All right? That's what we proved here. This is the generating function for all of these configuration. They all have this weight. bk can be anything. Okay? Now, in summary, let me copy this so that we have all the formulas. So this is something that we proved before. Now, we can reverse this formula so that we get lambda in terms of mu's, b in terms of mu's. So obviously, if you divide this by delta n minus 1, you can delete all the things. So lambda 1, lambda n is going to be this divided by n minus 1. Okay? You can just cut all the things except one of them. That means, what is lambda n? You can now divide this by same thing with n divided by n decreased by 1. So this is, you divide this by this inverse. Okay, that means delta n minus 2 over delta n minus 1 squared. But see, this is a determinant of moment. So everything is in terms of mu. So this is a formula that we can compute lambda n using mu's only. And also, what about b? Because of this, b0 plus dot 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 bn equals delta n prime over delta n. So of course, this is going to be this minus this. So corollary, just a summary of this, lambda n, delta n minus 2, delta n minus 1 squared, bn delta n prime, delta n minus delta n minus 1 prime, delta n minus 1. So everything in terms of mu, everything in terms of mu. So we can compute lambda and b using mu's. So it's kind of an explicit formula. Okay. Right. Yeah, there's a nice corollary, which we actually proved earlier this semester using just orthogonal polynomial theory. So let's say mu n is a sequence of number. Then the question is this a sequence of moment sequence for orthogonal polynomial OPS? Then there is an OPS with moments mu n if and only if the Hankel determinant is non-zero for all n. This is something that we prove using orthogonal polynomial theory, but we can now prove this combinatorially too. So proof. This direction. But let me recall you. But recall Pn OPS if and only if they satisfy three-term recurrence with lambda n non-zero. This is something that we proved. The Fabard theorem or the inverse. Yeah. So in this direction, now when you prove this direction, this is Pn is OPS. So OPS, that means lambda n non-zero. But this immediately implies that this is non-zero because you see here this formula, where is it? This is the product of lambda, so these are all non-zero, so of course this is non-zero. So quite easy. The other direction. This is also immediate, but lambda n, if lambda n is non-zero, we can define lambda n mu n, bn using the theorem on the left. We just define our corollary, maybe corollary above. Using this, because this is non-zero, denominators are non-zero, we can define lambda n bn like this, okay? Then, now we have sequences lambda n and bn. Define Pn using lambda n bn, right? Using the three-term recurrence. So we can define Pn, but then the moment is going to be a generating function for the okay, maybe I can just must be mu n, because mu n and the relation between mu n and b's they satisfy all the relations that they have to satisfy, and their connection is 1-to-1. So you can compute the moment, then that moment must be exactly this moment, because this 1-to-1 correspondence between lambdas and mu. So that's it. So we found a orthogonal polynomial having exact moment that we want. So that's basically the proof. Okay, and let's see. Right, now we're going to consider some special case. Now suppose Bn equals 0. Lambda n must be non-zero, but Bn could be 0. But Bn is 0, then something interesting happens. This is a simpler, we have a nice situation. And then recall there was a condition Bn 0 for all n, if and only if the odd moments vanish for all n. This was the theorem that we proved before. So then what happens to the Hankel determinant? So let's see, for instance, lambda 3 is the determinant of, I'm going to write just the exact determinant, mu1, mu2, mu3, mu4, mu2, mu3, mu4, mu5, this. But we know that the odd moments vanish, so it's going to be, maybe I can just write down over here. So these, they disappear. You can ignore them. You can treat them all 0, okay? So, but what is a determinant? What does a determinant do? You select entries, one entry from one row and from one column, right? Without any, so for instance, like this, I don't know, something like that, or yeah. But the point here is that, yeah, I think it's, let me just delete them because it's easier to see them. Let me just delete them. If you think about it, these 4 and these 4 are kind of separated, right? So you have to select, in this, you have to either select this or this, and either select this or this. They are independent of each other, selecting the points. So in other words, and they also keep their signs. So this is mu0, mu2, mu2, mu4 for this. And also times the other 4 entries. Okay? You can write it this way as a product. And also let's compute mu4. But if you do this, I'm going to now skip the zeros, or mu0, odd integers, odd moments are all 0. And finally, it looks like this. But again, this, it's like a checkerboard. And these, they don't affect each other. They are kind of separated. So this is a determinant of mu0, mu2, mu4, mu2, mu4, mu6, mu4, mu6, mu8, and the determinant of mu2, mu4, mu4, mu6. But this pattern continues. So in general, so let's say we're going to define, so let delta, so I'm going to use this notation, delta n. This is the usual Hankel determinant, but if I have of 2, this is exact the Hankel determinant, except I'm going to multiply 2 everywhere. ij 0 to n. Just like these. And also, let me use this notation, plus. Exact same thing, except we add 2 there. Okay? Just a notation. Then, in general, delta 2n, like this, is, what is this? This is delta n2, this is n minus 1. So this 2n is delta n2, delta n minus 1 plus 2. Okay? And this delta n2, delta n plus 2. So you always have a situation like this. So now, see, we have a bunch of zeros, but the zeros all disappear, so we have only those compact matrices, no zeros. So the question now is, can we evaluate this? Just these are the usual Henkel determinants, so we know what they are. But what about this? Can we compute this separately? And the answer is yes. First of all, because we have this assumption, so odd moments vanish. We have only even moments, and the even moments is originally was a generating function for Marchkin path, but we only need to consider Dick path. So mu 2n is the generating function for all Dick path of length 2n and the weight on the down steps. So we define A and B. Oh, sorry. From 0. Oh, I think did I start from 0? Oh yeah, this is obviously a typo. And yeah, here this should also be from 0. Yeah, as you can see from this. Okay. I think that's it. So here, where AI is now instead of minus I, we have minus 2i. B 2i, just like that. Then mu 2i plus 2j is of course the Dick path, generating function for Dick path from AI to bj, the weight of p. This is bi. So by the Lindstrom-Gesell-Vienno lemma, this n2 is the determinant of this mu 2i plus 2j, 0 to n. This is equal to sum over all non-intersecting lattice path from A's to B's, sign and weight. So again, let's look at this. I'm gonna draw this. Now we have to double everything, so maybe I should, let me try to, maybe I should just change. I think this is time to change the template, Yes. A3, A2, A1, A0, B0, B1, B2, B3, like that, okay? So now you go this, or this, something like that, okay? Again, this is fixed. We have now, we cannot go horizontally, so we have to go up or down always. So you have to go up, no choice. You cannot go down because of this, so you have to go up. Again, this has to go up, up. We have no choice but going all the way up. Same here, because we don't have any horizontal steps. Then this is also fixed. This is the only way that you can reach to B2, and this is the only way that you can go to B3. And what are the weights? Lambda 1, lambda 2, lambda 1, lambda 2, lambda 1, lambda 2. So n of them, lambda 1, lambda 2, and lambda 3, lambda 4, lambda 3, lambda 4, and then lambda 5, lambda 6. This is the only path in the non-intersecting lattice path, right? Because we don't have horizontal steps. That's the important part. So that means this only one, the sign is plus product of all of this. So it's like lambda 1, lambda 2, n, lambda 3, lambda 4, n minus 1, and the 2n to the first. Okay? So delta n of 2 can be computed this way, but we also have to compute this because we want to know that as well. Lambda n plus 2, let's consider that. Maybe I can just copy the whole thing. Let's see. So yeah, I'm gonna define, where is it? Yeah, I'm gonna define, just to tell you the difference, B plus. Yeah, right, everything is B plus. Where B plus is exact same, except plus 2. Okay? Then of course, this plus 2 is this. Okay? So this is this, but that is exactly this, right? Of course, we have to change this. And let's change this a little bit. I'm going to start over. The point here is that they all shift. So the A0 is here, but B0 plus, B1 plus, B2 plus, B3 plus, like that. Now we need to go from A0 to B0 plus. We have to go up. This is the only way. But so yeah, actually these are all decided. But first, they're all up steps, all fixed. Now this is the only possibility. This is the only possibility to go to B1 plus, and this, and this. Okay? So again, we have only one way to connect them, non-intersecting way. What are the weights? Lambda 1, lambda 1, lambda 1, lambda 1, and lambda 2, lambda 3, they appear like this. They appear in pairs. Lambda 4, lambda 5, lambda 4, lambda 5, and lambda 6, lambda 7. Only one possible path. So this is equal to, so lambda 1, there are n plus 1 of them. So in this case 3, n equals 3, but we have 4. But now this, we have n minus 1, n minus 2, etc. So lambda 2, lambda 3, n, lambda 4, lambda 5, n minus 1, lambda 2n, lambda 2n plus 1, 1. This is the other determinant. Okay? So corollary. Corollary. If p is 0, of course for all n, then lambda 2n can be written using those kind of double Hankel determinants. Lambda 2n plus 1, lambda n plus, lambda n minus 1, proof is really just a computation, just compare these two. Compare this and this. If you divide this, then you get only like one. We have some bunch of factors. So if you divide this by this, then only the odd factors appear, the remaining. And if you divide this by this, n minus 1, then only the even indices appear. Therefore, if you want to get this, just divide this by the same thing with n decreased by 1. If you want this, divide this by the same thing with n decreased by 1. But that's exactly this and this. So that's the proof. Okay. So we have a formula for lambda using only mu2n involved here, without using zeros for the stuff like that. So we have seen several examples of the applications of the LGB lemma, but like I said, most of the time the important part is the setup. Once you set up things nicely, then everything is just quite nice. And the proof goes like almost free. You will see some examples or in the homework problems. So in the homework problems, you just have to set up the graphs and the weights in a way that you get a nice LGB lemma applicable. Okay, so this is the section 7.3, and the next section we will see some kind of duality between Matchkin path and the Fabard path using LGB lemma again. And we will do that in the next section, so next time, so I'll finish here. Thank you for your attention.